Okay, well, we'll call the roll online then. Harrison's not here yet. Justin's not here yet. Nathan's not here yet. Tyler, Elijah, Terrell, Jeremy, Clark is here. How many times have you been top of the alphabet? Okay. Diamond, not here yet. Nakoma, Taiwan, Kenesha, Angel is here, and Brianna's here, right? Okay. Hopefully some of the others will be coming in. Okay, announced about the math team. Mr. Rossi is always looking for that, and if you want to have any practices here, see me, but I'll announce the part of that later. Tutoring, we have several resources here on this campus and on Birmingham campus. I have the Space Center schedules up here. They may have actually been modified since these were printed, but I highly encourage you to provide tutoring as well as receive tutoring if you need it. Certainly y'all are some of my most skilled students that could do a great job of tutoring. Graduation, I don't think any of you are graduating this term, but if you know of someone who is, the last of the graduation meetings is today at 1:30 on the Birmingham West Campus in the ACAP building, first floor theater. We've already had two already. That's that. All right. Now, let me add my current announcements. I meant to say this, I don't think I did on Monday, but let me tell you now, my office hours have changed big time, okay? Because second mini term began yesterday. So, my Monday, Wednesday office hours used to be 7:45 to 9:30, still are. 11:15 used to be 11:15 to 2, still are. Used to be 3:15 to 5:15, are not, okay? I picked up a second mini-term physics course on the Birmingham East Campus that starts at 4, so my class gets over at 3:15 here, so as soon as that class is over, I've got to book it and get everything ready to not only to teach the class over there, but to take home and everything, and because I'll be leaving from there and going straight home. So basically I have almost no time. Maybe a 15 minutes max between 3:15 and 3:30, but I've got to leave by 3:30 to make it there by 4. Well, usually I can make it a little sooner than that, but I always allow myself 30 minutes. All right, now Tuesday, Thursday. Used to be 10:45 to 5:15. Not completely. 10:45 to 1:15, because I also picked up a second mini-term physical science class that meets from 1:15 to 3:45 is the class, and 3:45 to 5:45 is the lab, and then I'm going home after that, okay? So it usually takes me 15 minutes to get everything shut down, back to the office, especially if we're doing labs. So I usually won't even leave by 6, but that's what I'm trying to. I'll try to get these changes made to your syllabus and also to the locator card on Blackboard. I can't tell you when that's going to happen, but I'll try to get it done as soon as possible. Okay, and then one other, I'll go on and hit it now. Well, I'll wait till others come in, and then I won't have to say it again. Let's pick up where we did last time. First, I want to know any questions on anything we've done so far. All right, if not, here's a little comment. We were just starting implicit differentiation. We had done examples 1 and 2, and then there was this slide that's at the top of page 146 in Chapter 2. Chapter 2, Differentiation, 2.5, Implicit Differentiation. It is meaningless to solve for dy dx, or d by dx of y, in an equation that has no solution. For example, x squared plus y squared is equal to -4. Can't. Not with x and y being real numbers, okay? Cannot happen, okay? So therefore, don't try implicit differentiate on that. You can do it, but it makes no sense because there are no solutions for that equation. If, however, a segment of a graph can be represented by a differentiable function, then dy dx will have meaning as the slope of each point on that segment. Okay? I think you can easily imagine the square root function. Okay? The derivative is not defined at 0 because that's an infinite slope there. But every other portion of that, as long as you don't include 0, yeah, you can do it. So just because a function is not solvable at one point, okay, if there are some points where it is. Recall that a function is not differentiable at two things here: points with vertical tangents, that's what I was just describing, and points at which the function is not continuous. So if you have a function that goes up here and breaks and then does like this, it can't be continuous there because the left and right hand limits are not the same. And the value of the function is not the same. Okay? All that stuff we did back in chapter 1. So here's example 5. We need to be doing example 3. So let's do example 3 first, and then we'll come back and do example 5. Okay. If possible, represent y as a differentiable function of x. Okay? X squared plus y squared is equal to 0. If possible, represent y as a differentiable function of x. What you think?
Could you square root everything?
Okay. If you were going to do this, I think I would subtract x squared first and then try to take a square root, wouldn't you? Okay, so let's try that first. Okay, let's minus x squared from both sides, and then you have that y squared is equal to minus x squared, and then what? Then take a square root? Okay. I'll know what the left-hand side would be. That would be y is equal to plus or minus the square root of minus x squared. Right? Anything wrong with that picture? Any bells or whistles? Oh!
You can't have a negative.
Right, and x squared is always going to be positive. You negate that, it's always going to be negative. You cannot take the square root of a negative number. Now let's back up and see what was wrong at the very beginning. What are the possible solutions to x squared plus y squared is equal to 0? Yes, x equals 0, y equals 0. That's it. The origin. 1 point. Okay? I don't believe it makes any sense in the... okay. I was thinking for y to be a differentiable function of x, if the function only has 1 point, how can you determine the slope of that point? You can't, okay? So no, that one should not be possible, okay? The graph of that is a single point, so it does not define y as a differentiable function of x. It defines it as one single point. About this one, x squared plus y squared is equal to 1. Okay? Can you represent y as a differentiable function of x? I think your original idea might do okay here. Subtract x squared from both sides, and that gives you y squared is equal to 1 minus x squared, and take a square root of both sides. Y is equal to either plus or minus the square root of 1 minus x squared. Okay, now since 1's a positive number, all this does is restrict your domain of x to something between plus or minus 1. Because if it's in between that, you can do it. If x was 3 or -5, no, you can't do it, okay? But as long as your x is restricted to the domain, some portion of that. Now, is that a function? Not with the plus or minus in there, okay? Because for any x, you could get two y's. You get a positive y or a negative y. So again, you have to restrict your range this time. You have to restrict the domain of x to be between plus or minus 1, and then the domain of y, or the range of y, to be either the positive side of that or the negative side, but it can't be both. Okay? Now, and again, if you go back and look at the original equation, x squared plus y squared is equal to 1, what does that represent?
A circle.
A circle of radius 1, right? And a circle of radius 1, unfortunately, is a very pretty, regular graphic, but it's not a function because the vertical line test fails in everything between plus or minus 1. Not at plus or minus 1, it only has one value, but anything in between. Outside, it has no value at all. So therefore, you can define a differentiable function of y either to be the top half of that circle or the bottom half of the circle, but it can't be both. Okay? Now let's see how they say it. The graph of this is the unit circle centered at 0, 0. The upper semicircle is given by the positive of that when 1 is between, or x is between 0 and 1. Now, there's no reason to exclude, and they don't in the graphic, but there's no reason to exclude -1 and +1. Those should be or equal to signs, less than or equal to signs. Because it's perfectly okay to have that. And the lower semicircle is given by the minus of that. Oh wait, here's they say, at the points, okay, this is why they excluded, I forgot. We said a differentiable function, okay, sorry about that. It's not differentiable at the endpoints. It's defined at the endpoints, but not differentiable because they're in your vertical tangent lines. So yeah, they were right, I was wrong, okay. Differentiable functions, you would have to exclude that. The function is defined there, but it's not differentiable except between -1 and 1, not included. All right? The C one. X plus y squared is equal to 1. What would this, can you, what is this? If possible, represent y as a differentiable function of x. Okay? Sort of like we were saying before, to start with, look at that and say, yes, this does have valid points. The first one didn't, the second one did. Does have valid points. So let's give it a shot. So what would we do first? Subtract x from both sides, and that gives us y squared is equal to 1 minus x. And then what? Square root of both sides. Y is equal to, and again you have to do the plus or minus deal, the square root of 1 minus x. Anytime you take the square root of both sides of an equation, one side or the other, you got to have that plus or minus in there. Okay? Now, again, that is not a function. Okay? However, either one of those would be a function. Y is equal to square root of 1 minus x, that's okay, and y is equal to minus the square root of 1 minus x. Both of those are functions. Okay, now the domains of these functions, and this one too, but it's not a function, the domains have to be that this thing inside has to be
between 1 and -1.
Okay, -1 doesn't work here.
Oh, yeah.
Because it's not a square, okay? Wait, no, -1 does work there, in fact. Well, here's what you do here. What But this says this thing in here has to be greater than or equal to 0, right? Can't take the square root of a negative. It has to be greater than or equal to 0. Okay. Here we have okay. Good deal. Now we have enough students for a bridge table. Okay. Okay. So, rather than just waving my arms, let's do it this way. 1 minus x has to be greater than or equal to 0. Can't be negative. Must be positive or 0. Okay. Well, let's how would you proceed on that? There's two ways you can go. I don't want to tell you which way. I want you to tell me which way you would go.
For our domain.
Yeah, that's what we're determining the domain. What can you do to that inequality to solve for x? Okay, certainly that's one way to do it. Subtract 1 from both sides, and that gives us
Negative x, that's greater than or equal to negative 1.
perfect. Say again?
Divide by negative
1. Okay, either multiply or divide by negative 1, and that gives you x is less than or equal to 1. Okay. You see why? Because you can add or subtract any positive or negative number to both sides of the directional inequality, whichever way it's pointing, no problem. You can multiply or divide both sides of the directional inequality by a positive number, no problem. But if you multiply or divide a directional inequality with a negative number, either multiplying by negative or dividing by negative, flip the direction of that inequality. Okay? So that's what we did there. So x has to be less than or equal to 1. So it's anything from 1 south. You know, any negative number works. 1 works. 0 works. Everything works except anything greater than 1. If it's greater than 1, it doesn't work because it makes that negative. And that goes for both of those. Okay? So, with that restriction to your domain of either one of those, do we have differentiable functions?
Yes.
With one exception. You have to take out the minus, because at x equal negative 1, that becomes 0, and it has a vertical tangent on it. So it's not differentiable at x equals 0, but everywhere south of it. I mean, at x equal 1. But everywhere less than 1 if it's differentiable. Okay. So you actually have two of them, two functions that would work. You just can't include one at either one. Now.
So why would we not make the domain just less than 1?
Yeah, well, the domain of that function would be less than or equal to 1. The domain of the differentiable function is less than 1. Yeah. If you don't have that the adjective differentiable in there, then it's okay. But if you do have it in there, 1 is not okay. Okay. Enough for a basketball team now. Okay, good deal. Justin's here. All right. That was example 3 on page 146. That was sort of the top half of the page, kind of. All right, to erase. All right, let's do example 4 before we go to example 5. And this example 4, it says, see larsoncalculus.com for an interactive version of this type of example. So it may not be exactly this one, but similar. Determine the slope of the tangent line to the graph of x squared plus 4y squared is equal to 4. At the point root 2, okay, I was having trouble reading it, root 2, comma, 1 over root 2. Okay, now, cynic that I am, I want to make sure that point is even on that curve, on this, the graph of this thing, okay? So let's plug and chug and see if it is. If you plug in a root 2 for x and square it, and add to that 4 times 1 over root 2 squared, is that equal to 4? What is root 2 squared? 2. Plus 4 times, and what's 1 over root 2 squared? Say again? That 2's in the denominator, right? Isn't that 1/2? Okay, is that equal to 4? Well, half of 4 is 2. 2 plus 2 is 4. Yes. Didn't know we'd be doing such high-level math today, did you? 2 plus 2 is 4. Okay, y'all are good. Okay. So, yes, that point is on the curve. So, I'm going to, that was all to verify and make sure it was. So, I'm going to take that out of here so we can proceed with our problem. Now, the problem was determine the slope of the tangent line at that point. So, how are we going to determine the slope of a tangent line? What's going to give that to us? Ah, yes, I was going to say we need to ask the right question. I mean, give the right answer. Okay, okay, always right answer. Not always, but most of the time. So, how do we take a derivative of that? How do we take a derivative of that? Say again? Foil it? Is that what you said? No, there's no product here. You foil with products of binomials. Ah, yes, we take a derivative by with respect to x, and that would be 2x next plus 8y dy dx. Chain rule. See, x is, derivative of x with respect to x is 1. Okay, so you don't have that. But since y is a function of x, are we assuming that, then you do first the derivative of the outer function, then the derivative of the inner function. And then z equals 0 because derivative of a constant is 0. Now what? Say again? Yeah, you're trying to solve that for dy dx. That's exactly what you're trying to do. I was just about to draw the arrow there. That's what we're trying to do. Solve for dy dx. And how do you do that? Not yet. Subtract what? 2x from both sides. Okay? And that gives us 8y dy dx equal negative 2x. Next. Now divide by 8y. Perfect. Okay? 8y's go out here, and that leaves dy dx is equal to, let's simplify that a little bit, minus x over 4y, or 1/4 of x over y, or however you want to say that. Okay? Now, that gives you dy dx. And all they asked for was the slope at this point. So guess how we get the slope? that is dy dx evaluated at the point root 2, 1 over root 2. And what would that be? I'm going to pull out my minus 1/4. I just don't like having that in the way. And your numerator here is your x, right? That'd be root 2. Your denominator is 1 over root 2. Now, it's a little messy, so let's kind of clean it up a little bit. Negative 1/4. Get out of there, okay? And what I'm going to do here is a division, root 2 divided by 1 over root 2. I'm just writing that division horizontally rather than vertically. But that then is minus 1/4 times root 2. Change that division to a multiplication, and then what do? You flip it. So that would be times root 2. Well, what's root 2 times root 2? 2. So this would be minus 1/4 of 2, which is negative 1/2. So that's the slope at that point. Okay? Now, I wish this book, I've taught from him before, and always before in the pre-calculus, they had all the figures in there too, so you can see what they're talking about. This one, he only does the examples. He doesn't show the figures. I kind of hate that, because that means I have to draw the figures, okay? So, now this is a little bit beyond what this course is about, but I'm going to go on and do it anyway. One way to, oh, the 10 o'clock scholar, okay, Terrell is here. Good to have you. Okay. All right. Now, actually it'll be Cal 3 before you do this, I think, but let me go on and show you. Let's take this original equation here without the error in it, okay? And let's divide everything by the constant, 4. And what that'll give you is x squared over 4 plus y squared is equal to 1, okay? Now I'm going to do something else here that you might find a little bizarre. I'm going to write that as x over 2 squared plus y, I'm going to put it over 1, which is strange, but squared, is equal to 1. Okay. Now, Chaston's here. Good deal. We're slowly getting a good class size here. Always had a good class. It's just good class size. All right. When you, at the very beginning of Cal 3, you're going to learn that's, well, actually, not quite. You'll be reminded of this. I don't remember if you've had conic sections before. Have you? Okay. I was afraid of that. What this is describing here, this is sort of the standard form for one of your conic sections. And there's several conic sections. A circle is 1, an ellipse is 1, a parabola is 1, and a hyperbola is 1. This is the standard form for an ellipse, where that's the standard form for the ellipse. I forgot where I wrote it. Where 2 is your major axis, 1 is your minor axis, and the plus is in between here. That gives you an ellipse. So that's why on the side of your page here, the margin, figure 229, that they don't show in the slide PowerPoints, which I don't know why. You can see that the x-intercepts are minus 20 and plus 20, and the y-intercept is plus 1, 0, 1, 0, minus 1. Okay? And that's a closed curve called an ellipse. Now, the point in question is this one. Did I? Oh, I did. I'm sorry, wait a minute. I left off a minus sign. Whoa, I can't write with my pen on the screen, okay? That's a minus there. I missed the minus sign, sorry folks. So then in the y here, we'd have a minus here, and then this would be minus there, and that would be a minus. I don't even see where, oh, here it is, yeah. That would be a minus there, that would be a minus there, and that would be a plus there. So your slope is 1/2, not minus 1/2. Sorry about that. Okay, I was wondering, why are they down in the fourth quadrant? And I saw, whoops, okay. The x value is √2. There are two possible values there. They're doing the one on the bottom, the -1 over √2. Y is negative, okay? So that gives the slope that's positive 1/2. Okay. When they give you a specific point, you remove the ambiguity of which value. Because that's not, I was going to draw it here, but I started talking about the book. That's 1, 1, negative. Here would be your ellipse. Something like that. And we're down here. Something around here. Positive 1/2 slope. Because we're √2, which is 1.414, and 1 over √2 negative, that would be negative 0.707, and or something about like that. And then you get the slope of 1/2. Sorry, it feels like my voice is leaving me. I don't know why. We've been together all these years. Okay. All right. Now, that was one way to do this problem. The other way would have been to solve this explicitly like we were just doing for y. And you can do that. First, you're going to subtract x squared from both sides. That would be 4 minus x squared. Then you'll divide by 4, and then you'll take the square root. Okay? And that will give you plus or minus 1/2 square root of 4 minus x squared. And because it's a minus for the y, you use the lower half of that. And here's the logic. Good deal. Okay. And that's what they remark at the bottom. Y is equal to negative 1/2 of the square root of 4 minus x squared. It's the other way you could have done that. Take it, and take the derivative of that, and you'll get the same result. I think it's a lot harder because then you've introduced a square root. You got to do negative fractional exponents, and this was so much cleaner doing it this way. Any questions? All right, we're just finished example 4. Bottom of page 146, chapter 2, differentiation, 2.5, implicit differentiation. All right. Now, any questions for our races? Okay. Let's do example 5. They had skipped 3 and 4, so we did those on the same page as 5. Now let's do example 5. Determine the slope of the graph of 3 times x plus y squared is equal to 100 xy at the point 3, 1. Okay? And again, the cynic that I am makes me want to check and make sure this point is in that curve. So let's see if it is. Let's plug the 3 in for the x. 3 squared is 9 plus 1 in for y. 1. 9 plus 1 is 10. 10 squared is 100 times 3 is 300. And if we do 100 times 3 times 1, 300. Yes, that point is on that shape, that curve. Okay. I always do that first just to make sure it's not an ill-posed problem. Asking you to do something that makes no sense. So how are we going to determine the slope of the graph of that weird-looking thing? How would you proceed? And there's several ways. What would you do? I'm sorry? You certainly could. That's a legal move in most states, so you could do it. I don't see it gains you very much. Okay? What would be another guess? You see, I usually don't care for fractions if I can avoid them. Now, you may love your fractions, so go for it if you want to, but if I can get by without fractions, I'll try to do that most of the time. Second? You certainly could do that too, especially after you divide it by 3 and then take a square root, and now you have a radical, which is you have to change to a fractional exponent, and there we have a fraction again, and I'm just way too lazy to do stuff like that. Okay? Any other guesses? And those are legal. You can do them. I just don't want to do them. Okay? Well, dividing by 3 isn't bad. No, not at all. What's another thing you could do? Let me... Oh, okay, what? Because all we're looking for is a slope. What's going to be the slope? Take a derivative. And how do you do a derivative of a weird-looking function like that?
Very carefully.
Yes, implicitly as well. Okay? I don't want to try to do that otherwise. Now, I will concede there may be one step you can take to make it a little easier to do, and I'm not sure even that's going to be true. You could square that binomial if you wanted to, but frankly, I see no huge advantage of doing that. Okay? But we could, if you want to do that. That one I would consider maybe doing. Okay? But which way you want to do? Square that first, and then implicitly differentiate, or implicitly differentiate just like it is? You tell me. Help me, help me. Say again? Okay, actually do the squaring. See, that's not going to introduce anything that's too awfully bad. So let's leave the 3 out front. And what's the square of x squared plus y squared? X to the 4th. Okay, certainly there's going to be a y to the 4th. But have you left out something? Hint, there's a gap there. Plus remember, when you're squaring a binomial, square the first, twice the product of the 2, square the second. You could go over to the side and FOIL it. Someone wanted to do that earlier, right? You certainly could do that, and you'll get that answer. Okay? I'm not saying this is any easier, but it is a possibility. And that's equal to 100 xy. Now, we implicitly differentiate. Okay? And what does that give us? Now, if you're going to do that, then I think you're probably better off going and multiply through by the 3's. 3x to the 4th plus 6x squared y squared plus 3y to the 4th is equal to 100 xy. Okay? Now, explicitly or implicitly differentiate. What do you get? 12x cubed plus
12x
No, y squared. Remember, product rule?
Yeah.
Yeah, that's the product rule here. Okay? So that's the first half of it. What's the second half? 12y. Second?
Shouldn't it be times instead of plus?
Okay. Let's go back to x times sine of x. Okay. Don't you first times root of the second plus second times root of the first? Yeah. So that's where the plus comes from. What you did here was derivative of the first. I was just writing down what you said times the second plus the second times the root of the first.
Well,
And
that's because
what's that?
there's 3 sections in this one instead of usually 2.
Yes, there's yeah. You have a product rule right here in the middle. That's one reason I tended not to want to do this, but it is legal to do it. So you did 2 times 6 is 12y x squared. That's the
Right. It's like
yeah. The first is, this one is the derivative of this times that. The derivative of this is 2x squared. No, right here, I'm sorry, right here. The derivative of this is 12x times y squared, and then the derivative of this is 12y times x squared. So we got one more thing to do here. Yeah.
Oh, dy
dy dx, exactly. Okay, dy dx. Because chain rule inside the product rule, okay? Plus 12y cubed dy dx. Okay, I've run out of room. This is equal to 100
next one. Oh no, it would be 100 y
y.
dy dx.
Okay. All right. Again, it's a product rule. Okay. Now you can pull the 100 out, or you can keep the 100 in. I don't care which way you do it. If you're doing the derivative of the first times the second, that would be just 100 times y. That's what I thought you were doing. Then the product rule says you do then the first times the root of the second. So that would then be also 100x. There you have your dy dx. Sorry, my sister, I think, got me for Christmas, one Christmas, we were young. There's a little block, and it said, plan ahead. Okay. In other words, I didn't have a long enough block to write the words in, so I didn't plan ahead. So I didn't plan ahead over there. I don't have enough room to write things, so sorry about this. It has nothing to do with calculus, does it? That was just dumb. Okay? Now, if you picture this all spread out then, what are you going to do next? We're looking for the slope, which we find with dy dx. So therefore, let's isolate the dy dx's. Here I have a term in dy dx on this side. So basically, I'm going to subtract 12x cubed from both sides. I just don't have any room to do it over here. Okay, and I'm going to subtract 12xy squared from both sides. Okay, and I'm going to subtract 100 x dy dx from both sides. Ew. I'm going to put it over here. 100 x dy dx. Ew, this is awful. Okay. All right. So these go away. Those go away. That's going to be subtracted. And this goes away. Okay. So what are we going to have left? A 12y x squared dy dx plus 12y cubed dy dx minus 100 x dy dx. That's going to equal to what's left on the right. What's left on the right, is 100y minus 12x cubed minus 12xy squared. Right? Okay. Believe that's right, right? Okay. What do we do next? Okay, do y'all see? I almost feel like there's some snickering. Do you see what we've done here? I know it's ugly, but have you followed it? Huh? Yeah, okay. Okay. All right, so that's what we got. What do we do now? What are we looking for? The slope which we get from the what? Dy dx. So what we have to do over here is isolate the dy dx. So let's factor it out of every term. Dy dx, and what are you left with? 12yx squared plus 12y cubed minus 100x, right? And that's equal to 100y minus 12x cubed minus 12xy squared, right? Now what do we do? What we want is that, right? So what do we do? Yeah. This thing is multiplied by that thing. Yeah, divide by that thing, okay? So we're going to divide both sides by 12yx squared plus 12 y cubed minus 100x. That'll divide this by 12yx squared plus 12y cubed minus 100x. Okay? That leaves us our dy dx. All we have to do now is evaluate this at the point 3, 1. It's gotten so messy up here. Yuck. Why is the eraser? There it is. Okay. Okay. At that point, 3, 1. At this point. So, dy dx evaluated at the point 3, 1 is equal to, takes a while for the PowerPoint to catch up, So plug and chug. What do you get? That numerator, first term. 100. No, the y is 1, right? Okay, minus. Minus what? Help me, help me. 12 times 3 cubed. You want to know what 3 cubed is? 27. So 12 times 27 is? Second? 324? Okay, I'll take your word for it. 324. Okay, minus 12 times 12 times 3 is 36, times 1 squared is 36. Okay, that's your numerator. What's your denominator? 12 times 1 times 9, right? 12 times 9 is 108, isn't it? Okay, plus 12 times 1 is 12, minus 100 times 3 is 300. Okay, I hope someone has a calculator and can do that so I don't have to. It looks fairly weird, but it seems like it's coming out okay. Let me try it. That would be minus 360 plus 100 would be minus 260 divided by 120 minus 300 would be 180, negative 180. Is that right? That'd be 26 over 18, which is 13 ninths. And that's what they got. Yay, I love numbers like that, okay? Nice round numbers. Okay. Now, I hate to do this, but I'm going to, because it already has taken so long working this one problem. I want to do it the other way, okay? Not multiplying first. And you tell me what you like better, okay? All right. Now, not multiplying first and just taking the derivative implicitly would be 2 times 3, which would be 6, times x squared plus y squared to the first power, right? That's just a power rule. Times the derivative of what's inside, which is 2x plus 2y. Say again? 2y. Chain rule. dy dx. Every time you do a y, you have to chain rule it and do dy dx, because you're taking derivative with respect to x. You don't have to do that for x's, because d by dx of x is 1, but d by dx of y is dy dx. Okay? So that's the left-hand side. Already it's looking a little easier, don't you think? Right-hand side is what? 100. Y, why not? Plus, product rule. Second? Not yet. Okay. Now what I thought you were doing there is a product rule, and you did 100 times the derivative of x is 1 times y. Okay? And now you got to do the other one, which is 100 times x times dy dx. Okay? Product rule. Okay? So that'd be 100 x dy dx. I almost ran out of room on the shortened version here. That's not nice, is it? Okay, now, here's where things still get somewhat messy. We have a pretty significant thing to do, and what I'm going to do first is notice there's a factor of 6 here, and I can factor out a 2 from both of these. That's going to give me a 12, okay? And what I'm going to do here is then multiply what's left, and this was, if I factored out the 2, this is just x plus y. I'm going to write it y prime because I don't like writing dy dx a lot, okay? So I'm going to multiply, FOIL those two, okay? So that's going to be x cubed when I FOIL those two. That's the first. The outer is going to be this one plus x squared y prime, if you'll excuse me doing that. Then the inner is plus y cubed y prime, and then the last is plus, I think I did it wrong. Yeah. Oh, I didn't do the inner. Yeah, I was doing the outer twice. Okay. Let me back off a moment here. I drew my loop in the wrong place, and that threw me off. The inner here is 2, oh, I already did the 2. X y squared. Okay. Let me clean that up a little bit. I cleaned it up too much. Okay. And then the last is what I just had, plus y cubed y prime. Okay. I'm just shortening that a little bit. And this is equal to, I'm going to factor out my 100 also, and leaves me with, no, I don't want to do that, do I? No. Sorry, wait one. I'm going to leave that 100 y plus 100 xy prime. Okay. Now, I pulled out the 12, now I'm going to multiply through. 12x cubed plus 12x squared y prime plus 12xy squared plus 12y cubed y prime is equal to 100 y plus 100 xy prime. You know, now that I look at this, that was really dumb, wasn't it? I should have, well, I still can do it. I'm going to divide everything by 4. Is that okay? That make that a 3, make that a 3, make that a 3, make that a 3, make this a 25, and make this a 25. Why not do that? Get the numbers as small as possible. Okay. Now let's gather our y primes together. We're going to subtract a 25xy prime from both sides. Okay. And I want to subtract a 3x cubed from both sides. And that will go away. We'll subtract also a 3xy squared from both sides. And that will go away. Okay, I think we're ready to roll now. These are gone. So you have a 3x squared y prime plus 3y cubed y prime minus 25xy prime is equal to 25y, and these went away, minus 3x cubed minus 3xy squared. Okay. Now we factor out our y prime, which is what we're looking for, and we're left with 3x squared y plus 3y cubed minus 25 y, or x, not y. Ew. Is equal to 25y minus 3x cubed minus 3xy squared. Okay, and divide both sides by the 3x squared y plus 3y cubed minus 25x. Okay. And that's what your y prime is. Evaluate that. Get out of there. Okay. Evaluate that at 3, 1. I think we should get pretty close to what we had before. That would be at 25, because y is 1. Goodness gracious. Minus 81, right? 3 times 27 is 81, minus 9 over 3 times 3 squared would be 27 plus 3 minus 75. Okay? Now let's see how that does. What's that? Same answer. Okay. Thank you so much. Save me having to do it. Okay? I like that a little bit better. Okay? I did some messing around in there. I probably should have taken care of sooner, but yeah, it comes out a little bit neater. And they got, and they wound up doing it, I think, very similar to this. Yeah. They got that same thing. All right, any questions on that? By the way, what in the world was that odd-looking function anyway? It's called, now this again, I wish they had the graphics in here. It's called a lemniscate, okay? And I'm not going to graph it in its completeness, but basically going from okay, it basically does something like this. Yeah, I didn't get it very well. And at 3, 1, sure enough, that was on there, and the slope was 13/9. Ah, yeah, look at that line. I can see that's 13/9. Yeah, right. Can't you? Me either. Okay. But it's positive, and it looks like it's greater than 1. Okay? So, yeah, I'll go with that.
So you factor all of about 4?
Okay, where? Right here? This line? Yeah. I saw 12, 12, 12, 12, 100, 100. Every one of those terms is divisible by 4. So go on, get the numbers as small as you can. Okay? So I divided everything by 4. That gave me 3, 3, 3, 3, 45. And from there on, it makes a lot more sense. Okay. I probably could have done that in the last one had I noticed it, but I didn't really notice it in time. When I saw it here, it was just so obvious. All right. Let's delete all this, erase all this, and see how they did it. Okay, first, they did d by dx of both sides of the equation. And they didn't multiply through, thank you very much, okay? And this would be the exponent times the coefficient, 3 times 2, that's your 6, times what's in there, 1 less power, it's just power rule. Then, chain rule, derivative of what's in there, that's with respect to x, 2x, plus 2y, but then you got dy dx because y is a function of x is not a function of x. Okay. Over here, 100 on the outside, x dy dx plus y times 1. Derivative of x with respect to x is 1. You have to put that in with yourself. Okay. Now, they did the same thing I did. They said, notice that this is 3 times 2 is 6. And you have another factor of 2 here, that would be 12. Okay. There's the 12 times x squared plus y squared. That's good. Oh, they subtracted from both sides. They're skipping a lot of steps here. So this one is just 6 times this times this. So that would be 12 times y times this times dy dx. They're moving that one to the other side. Okay. And then they're pulling this one minus 100x dy dx from this side. And then they had the 100y here and subtracting the 12 x squared plus y squared times x. 12x times x plus y squared. So they did all that at once. Okay? Some point we got to pay the piper here, so here's payment time. Boy, I hate that. I wish they'd have done it on the bottom here. Okay, they factor out the dy dx, and that gave them a 12y times x squared plus y squared minus 100x. Okay, and that's what they got there. Dy dx is equal to, and they just left that side alone. 100y minus 12x, blah, 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 blah. Okay. Now, what they did next was divide both sides by what you had over here. And for some reason they reversed the order. I don't know why. I like this first, but they did. They just reversed it. Minus 100x plus that. So that's okay. Legal in most states. Okay. And then they plug in the value. Well, no, they didn't. They then divided everything by 4, just like we did. That made 100y minus 3x times that, minus 25. 25y minus 25x and plus 3 this. Okay, so they did that first. And then they plugged in 3, 1. And there's where they plugged in the 1 for y, 3 for x's, and went to town with it. And hey, they did show the graph here. Thank you very much. Okay, the limit over there is the 0.31 that we first determined, and when they did all their calculations there, they got 25 minus 90 over negative 75 plus 30. Why they reverse those, I don't know. Negative 65 over 45, which is 13 over 9. You divide both sides there by what? 5, yeah. Negative 5. Yeah. Got it the same way. So there's tons of different ways to work it, to go through it, the individual steps, but the answer for that one is 13 knots. And that is the slope at that point. 3, 1, that is on the curve. We verified that to begin with. The slope there, the tangent line is there. That is greater than 1, but not a great deal greater than 1. 1 and 4 ninths. Okay. Any questions? And that's called the limit-escape. Whoa! They have that being the last. Okay. Example in the slide set. However, there is an example 6 in the book, so let's do that one. Determining a differentiable function. Okay. Okay. Find dy dx for the equation sine y is equal to x. Okay? Then find the largest interval of the form minus a is less than y is less than a, for which y is a differentiable function of x. Okay? First thing they say is find dy dx. How would you do that? Help me. Anybody? Say again? I can't hear. I can't hear.
We're doing implicit.
Yes, implicit differentiation. How does that go?
Derivative.
Take a derivative.
So that'd be
Cosine
y
y.
times y dx.
Okay. I'm going to put the dy dx up front just to make it clear it's not part of the cosine. Is equal to? Okay. Oh, not that one. Ooh, that was the last one. We're through with that one. Equal to? 1. There we have it. Okay. So how do we get dy dx? Divide both sides by cosine y. Okay? And what does that give us? Unfortunately, they leave it as 1 over cosine y. You could write that as secant y, but I don't think that really helps you a lot. Or at least they didn't do it. Okay? Now, what they do here, which is legal and reasonable, they now graph this as if y is the independent variable, but it's still vertical, and x is as if x was dependent. And what you have there, a cosine, oh no, I'm sorry. They graphed the sine x. So I think we would, yeah. Sine y is equal to x. They're graphing this one, okay? And it starts at 0 and goes up to 1 at pi halves. When y is pi halves, your x is 1. And when y is pi, your x is 0. And when y is negative, you just have a sine curve doing it. Yeah, I don't draw very good sine curves, but you have one stretched out like that, okay? Now, sorry, my eyes are stinging like crazy. Okay. And the interval, find the largest interval of the form minus a less than y less than a, on which this is differentiable. Well, that would be from right here to right there. And this would be from minus pi halves to pi halves. Those are your a's in that thing that they did in the book. Okay? Now, You can't include the endpoints because here you have vertical tangent lines, so dy dx is not defined there. But anywhere from that, from minus pi halves to pi halves, not counting the endpoints, you do have something you can deal with there. Okay, and what they do is sort of clever here. There is your derivative, right? And what they're saying to do here is to take this and say that cosine y is the same as the square root of 1 minus sine squared y, right? Because cosine squared y is equal to, well, sine squared y is equal to 1, right? So you subtract sine squared from both sides, 1 minus sine squared, and then take the square root. Okay. It's okay. And they do mention also that cosine, the derivative here is positive everywhere, so cosine y is going to be positive, okay, from looking at the graph. So, but then from here, sine y is x. So this is also the square root of 1 minus x squared. Okay? So what we have now is dy dx is equal to 1 over the square root of 1 minus x squared. And that's what they leave it as. Okay? Here's what I was real tempted to do, but I wanted to check and see if they did it. I would have started off this thing, or at least thought about it anyway, of rewriting this and say that y is equal to inverse sine of x. And then you take the derivative of inverse sine, and you get exactly that thing right there. So to me, their approach was correct, but it would have been just about as easy to go and do that at the very beginning, and you're done for it. So, I don't know. I couldn't figure out why they were doing this. I kept thinking there's got to be some rational reason you didn't do it the other way, but I can't see that it was. Okay, sorry about that. All right, there was example 6. Let's move on to example 7. Oh, we don't have an example 7, do we? All right, let me clear the ink off of this screen. All right, and let's see if we can get example 7 done. And by the way, here on the on page 148 is a little blurb on Isaac Barrow. Anyone have any idea who Isaac Barrow was? He was, interestingly enough, he was Newton's teacher at, you might say major professor at, was it Cambridge or wherever he went. Newton was his student, and probably within just a few years, Newton had surpassed anything that Barrow could teach him. And so Barrow resigned the chair. He was the Lucasian chair of mathematics at Cambridge, I believe it was, and gave the chair to his student Newton because he had way gone beyond him. Interesting character. But anyway, he was a really good mathematician on his own right, but he just couldn't hold a candle to his student, The student went way past him, okay? So Barrow had a hand in developing calculus as well. He probably helped Newton out in some way or shape or form, but he gave his student the credit. Okay. With explicit differentiation, the form of the derivative also often can be simplified, as we just did, by an appropriate use of the original equation. Similar technique can be used to find and specify higher order derivatives obtained implicitly. So what we're going to do here is example 7, which is given x squared plus y squared is equal to 25. Any of you want to make a guess of what that is? What that equation describes? Circle of radius 5, you got it. Given that, find d2y dx squared. In other words, find the second derivative with respect to x. Okay? Second derivative of y with respect to x. So what might you do first? You're looking for a second derivative. What usually do you have to do first? Find the first derivative. How would you do that? 2x plus 2y. Second? Y is a function of x, so you have to do the chain rule. What do you get? dy dx. I'm going to do it this way because that's how they're going to do it, is equal to 0. You're right on that one. So now what do we do? Say again? Not yet. Let's do this. Subtract 2x from both sides. Okay? And that gives us 2y dy dx is equal to minus 2x. Right? And now, divide both sides by 2y. Okay? So we have dy dx is equal to minus x over y. Okay? Now we take a second derivative. And what do we get? d2y over dx squared. And I'm going to rewrite that as I like to do. Minus x times y to the minus 1. That, to me, is way easier to take a derivative off of this. I have to use quotient rule here, which is nice and has a catchy little tune, but it's so much easier to do it that way, to me anyway. If you like quotient rule, use quotient rule. Okay? What will that give you when you take the derivative of the second one? This one here. What do you get? Okay, x y to the minus 2 minus, it's sort of a plus, but you're going to have a minus show up, right? Yeah. Y to the minus 1, right? Is that right? Huh?
It'd be dy dx at the end of that, right?
I'm sorry?
Wouldn't it be dy dx after that?
Okay, yes, you certainly, wait. The dy dx shows up here because that's when you're taking derivative of y. It's minus a minus, which is plus x, y to the minus 2 dy dx. You would have a plus, but you already got a minus there too. Derivative of x with respect to x is 1, so it's just minus that. You see, this was the place you're taking derivative with respect to y. Here you're taking derivative with respect to x. The y didn't change that. So your dy dx goes there. Okay. Now, at this point, we can go back and plug in what is dy dx, which is this thing right here. Okay? So let's see what we got. X over y squared times a negative x over y, right? That's your dy dx, minus 1 over y, right? So this is going to be a minus x cubed over y cubed minus 1 over y. Let's see if that's what they got. Oh, wait. Ah, okay. One more step. Okay. Time out. Either I did something wrong or okay. Okay, they did the whatchamacallit rule, the quotient rule, which is fine, perfectly fine in most states, okay? But our answer is correct, okay? That is fine. But let's take it another step, I think, okay? All right. Let's make this multiply the second one by y squared over y squared, right? Is that okay? I'm sorry. That'll make a y cubed in the denominator. 1 over y is y squared over y cubed, right? So what we have here is a minus x cubed minus y squared over y cubed. Right? Yeah, okay with that? Now, what we're going to do here is minus x times x squared minus y squared over y cubed. I don't know. This isn't getting very far. I have an extra x from somewhere. I don't know where. Oh, my goodness. Let's forget all this, or a lot of this. Okay. Right down here, let's go back to what we had. Why did you let me get away with that? Okay. Whoops. Look at what you let me do. X times x is x squared, not x cubed. Whoa, yeah, what are y'all doing here, huh? Don't let me make dumb mistakes. Okay. Now it all works out. Okay. And now what we do is multiply in the second one, numerator and denominator, by y squared. So that would be a y cubed down here and a y squared up there. And that then gives you minus x squared plus y squared over y cubed, which is x squared plus y squared is 25. Negative 25 over y cubed. Bizarre but true. Okay. Dumb mistake. All right. But when I started off talking about Isaac Vera, he's a potential paper topic. Or the kappa curve, because he came up with that, wherever that is. And Newton is a potential paper topic. You know, there's just tons. Just in that little blurb, you can see several things show up. Now, all right, to erase that. Oh, I'm sorry. Sorry about that. What? I can't go back to it, but maybe I can answer your question.
2x squared plus y cubed, and then I didn't understand.
Okay, say that again now.
I said I was said plus, and I meant x squared over y cubed. There at the end, I didn't understand why we multiplied both by.
Okay, say what we had to begin with.
X squared over
x squared over
y.
y cubed minus 1 over
Well, no,
y.
the-
Wasn't
the start out with, here's what that started out with.
Okay.
That was my answer, was x squared over y cubed. That's what we started out with right there.
Okay.
I just didn't understand why we multiplied this out here.
Okay, I had a y cubed down there. Yeah. Okay. All right. This was x over y squared. That's a times there.
Oh.
I think.
Oh yeah, yeah, because it would have been times the
but yeah,
derivative.
because your time. Yeah, that's what it is. It's not a minus, it's a times. Yeah. Okay. That answer it?
Well,
Okay. Let's go back. Okay. Okay. So it wound up being this, didn't it? Because that was your, okay. Let me back up. Okay. I'm trying to recreate it in my mind, and my mind's sort of murky. Okay. So you had there we go. You had see if I can do it. A minus, no, we had a positive x squared over y cubed. Didn't we have that?
yes, minus 1 over y.
Minus 1 over y.
And then to get our final answer there, we multiply y squared.
Okay. Yeah. I'm trying to remember, was that a plus or a minus in front? That's a plus, it's a plus, it's a plus, okay? Right. Now, the question is, why do we multiply by y squared? Because I need a least common denominator. Least common denominator here is y cubed, right? So to get y cubed over here, I have to multiply by y squared. So multiply this by y squared over y squared. Because y squared over y squared is 1, right? Okay. So this would give you x squared over y cubed minus y squared over y cubed. Okay? Except I think this was a minus in front, wasn't it? I'm pretty sure that was a minus. Yeah, it was. But no. The way they're doing theirs is sort of wacko.
See what happened was we started out with a negative x times y to the negative 1 right here.
Yeah.
So then when you take the derivative,
Yeah, and that was a minus here, but then you multiply that by a minus here. Yeah, and that's where you get, yeah. So that's right, yeah. Okay. We're okay with that then. But then somehow
just because of the you end up with y squared plus x squared over y cubed, and y squared plus x squared is 25.
I think so. I think that's it.
That's
Yeah.
probably started out with.
Yeah, exactly. Right. And that came out being x squared plus y squared with a minus in front. So we got it. All right. Sorry we didn't get to do example 8. We'll start with example 8 next time. Sorry, folks. Now, I did kind of suggest or maybe even promised you I would have your test ready today. I don't. Sorry about that. You'll have to live the weekend without it. Can you? Okay. Maybe. Okay. Let me give you some homework exercises in 2.5. Sorry, sort of bogged down today. Homework exercises, any of the odds 5 through 19. All those odds are at calcchat.com, 5's at CalcView. Do either 21 or 23, they're both at CalcChat, 23's at CalcView. Do any of the odds 25 to 31, they're all at CalcChat, 25's at CalcView. Do either 33 or 35, they're both at CalcChat, but 33's at CalcView. By the way, you see some other names there. Agnesi, she was a very early, very famous woman mathematician. Descartes is there, so another one. Then either any of the odds 37 to 41, they're all at CalcChat, 39's at CalcView. You can explore the concepts with 43 if you like. 45 is another one, similar to one that we did, I think, so that has two parts to it. 47 is a CalcChat and CalcView, and then do any of the odds, these are second derivatives, 49 to 53. All three of those are at CalcChat, 53 is at CalcView. And you might want to hang off until we do the last one before you do any others. I'll assign those later. Okay? Good deal. Sorry, got bogged down a little bit with details today, but it worked out. And I'll try to have, knock on wood, your test ready for this chapter next time, Monday. Okay? Good deal. Sorry I didn't have it ready today, but I had a presentation to make Friday. I had 2 courses to get ready for mini terms this week, and I'm still working on the second one. So, miles to go before I sleep.
See you on Monday.
Okay.